students are gonna use like 50%. I can't tell. Turn on the other. Yeah. Totally, I'm sure. We had these others. So we have a straight hand right now. Yeah. My dad just drives me, so I just get to sit the passenger seat and keep it in sheets and on my ones. Yeah, I drove the there's like 3 different cars that I'm like, apparently I drove people the one had a super tire. Like, we saw that, we saw it. Oh, like, you want to understand that when you're aware, drive it's slower and you I was in one car accident. Water bad. Sometimes no. I like it. He's actually studying just on board.
Yeah, I think I'm good to start. Good morning. I'd like to just talk about test 4. Will be more than a month away. You'll have to wait until December 13th or December 17th. So usually this time slot of classes has a final exam period on the Friday, a final exam week, and that's the 17th. So if you don't have the conflict, you're welcome to come to the Monday, December 13th final exam period, which runs at the same time from 8 to 10 o'clock. You will not need the full 2 hours. Just test 4. It's not cumulative. Just test 4. Test 4 begins today, and there's 50 points. And you will get your test back today. I'll give you a bonus assignment, and you're handing in a homework today, which will be part of Unit 3 homework. You will get a Unit 3 homework slip before long. I also have a new homework set for you. I'll give that out at the end. I have 2 things to give you today: the homework set and your test. We're going to be starting our talk at something you received on Monday. Print copies have been printed just now. So if you're do you have this paper? If not, then I'll see where I'm going to put it. As a group, we'll be doing molecule problem A, B, and I put another one on the board that's E. Does anyone need a copy of this? Give you a moment to find it. So this is where the class broke last time, just after the rules were delivered on how to do the problem. Anyone need it? If not, we're going to get going. Takers? Oh, okay. All right, so here are the fill in the blanks. Try to make it as easy to see as possible. So in order to draw, as we had discussed on Monday, the enantiomer, a compound, given a compound, and this sheet has some compounds already on the paper. In order to draw an enantiomer, a molecule has to have at least 1 chiral carbon in it. This molecule could have 1 chiral carbon asterisk. It could have 6 chiral carbons. It could have 11. Can you imagine chiral carbons in it? It could have 3, 2, 1, 8. Just so long as there's 1. That means that an enantiomer exists and it can be drawn. Sound good? Went over this the last time. No objections? And in order to draw the enantiomer, as we'll get going soon, the thing to do is recopy the molecule in pencil. That's complex enough. There's a wedge here attached there. The main chain is 7 carbons. So let's just get that down on paper. That way we don't miscopy something and the answer is wrong to begin with. And then since enantiomer is opposite, since that's the case, inverts, as you'll see, all wedge hash couples. If you're given a molecule where iodine is on a wedge and hydrogen is on a hash, your answer will be iodine on a wedge but a hash, and hydrogen not on a hash but a wedge. So you have to invert it. All wedges and hashes. The full opposite, but the full complete 100% opposite would be all wedges and hashes. And it goes on. In order to draw a diastereomer, and remember, di is the bi is the half. Invert one or more, but not all carbon. So that's how you do it. But in order to draw a diastereomer, the molecule has to have at least 2 carbons in it. You could have more, but you need at least 2. The molecule you're working with could have 7 carbons in it. You could draw a diastereomer of it. Molecule could have 4 carbons, could have 2, could have 11. Can you imagine asterisks? That's 3 carbons to at least 2, right? At least 2 carbons in order to be eligible to draw a diastereomer, if one would exist. In order to draw a diastereomer, recopy the molecule pencil. And at this point, nothing's changed yet. It's just a straight recopy. And then what you do is, since in powder blue there, di is the bi is the hash. Since that's the case, invert one or more, but not all, as you'll see, wedge hash couples. Trying to get going on this then. I have, again, I have spares if you would need. I'm going to go over there now, providing I have all the pens. Oh, I forgot to do this. Anyone need a copy? Okay, so not to belabor this, this molecule has 2 carbons, so asterisked. Okay, so therefore I am allowed to draw the enantiomer, it exists, and I'm allowed to draw a diastereomer that exists because it has 2. Okay. Moreover, this next one has only 1 carbon. This is a geminal ethyl there, only 1 carbon. Therefore, I can draw the enantiomer, I'm good with that, but I cannot draw the diastereomer. And this problem here is one that I'll ask you to copy down because this is going to help with your homework, okay? If you copy that one down. So I'm sorry that looks like my learning tool could use a few updates and refurbishments. So this molecule, I'm asking you to draw at the bottom of the paper. And this molecule looks like a 5 carbon main chain for your homework, which I'll give you or at the end of class along with that test. So there's room enough. If only it was on there already, sorry. Looks like it's a 5 carbon chain. And in its particularness, you have a hydrogen on a hash at the 2nd carbon of the main chain and a hydroxy OH on a wedge. And for the middle carbon of the main chain, the one at the smack in the middle, you have an OH on a hash and an H on a wedge at the same vertex. And as you know from chapter 1, the wedge and the hash should be positioned close together. This molecule has a left and a right, a top and a bottom, and a front wedge and a back. You could hold it in your hand if you made the molecular model. It would have a dimension to it, 3 dimensions, wedge and a hash. And this molecule, this newbie, this molecule here has 2 carbons, so marked. Therefore, I can draw the enantiomer, the full opposite, and right, look at that, right, di. dies to 2. So there's your hint there. You need a threshold of at least 2 chirocarbons in order to draw a diastereomer. So looks like this could be the first thing asked for that test 4. Okay. And it says that that's over a month away. Is that test 4? So I'm gonna get going then. So okay, so I'm following that advice on the Word document. First task, I want to draw the enantiomer. I want to draw the diastereomer. Recopy them. Okay. I'm now imagine I'm working in a student blue pencil. Okay, this is a blue pencil. I'm working. This is ink off the copier in the hallway. I don't think you can buy something on Amazon which will erase ink, which is a pencil. I don't think there is. So you have to recopy it over here in pencil. This is like a tennis game because your neck's going back and forth recopying it, and nothing's changed yet. So 7-carbon chain, chlorine still on a wedge, bromine still on a hash. I have to recopy it again from the original. This is in pencil. Pencil is erasable. Chlorine, bromine later on a hash, it's up. So nothing's changed. It's just a recopy. So far, so good. Okay, I'm gonna now I'll do the part where enantiomer. Enantiomer, that's the hint to begin with a vowel, E. Enantiomer is the opposite. Invert all wedges and hashes. So here goes. I got a pencil. Gonna erase what's happening here. Erasing the chlorine. Scuff mark there, like a scuff mark, and it becomes a hash. Not done yet. That's not the full opposite. So for the bromine, it's on a hash, it's on a chirocarbon, erase that and put a wedge there. And you trigger a wedge there. And that's the full enantiomer. It's pretty cut and dry if you know what the problem is asking for. Any questions? Okay, for the diastereomer, and di is to bi is to half, invert one or more, but not all. So there's more than one right answer. We're just going to invert the chlorine and take it into from a wedge into a hash. There's an eraser mark there. Now it's a hash. Done already. And we'll do, looks like we're going to do problem B, and then there's this extra problem which will help you for, as you can see, your homework. Any questions? Looking for questions? I think you've done more difficult stuff than this. So here's again, this molecule has only 1 chirocarbon, so let's recopy it over. There was a hash, ethyl to the left, that was not chiral, and a wedge, ethyl to the right. Okay, so now it says 1 chirocarbon there. I'm asked to draw the enantiomer. What am I going to do? Enantiomer opposite. Enantiomer is the opposite. This used to be a hash. Now it's going to be a wedge. And this used to be a wedge. Now it's a hash. Erase that. Do you follow what I'm doing? Do you understand the principle of the thing? Okay. And there. I didn't need to invert this one. Didn't need to, because that's not chiral. I did it anyway. Will I be penalized? No. Didn't need to do this. But if you did it, it's not going to affect anything because so you have a geminal ethyl. You have 2 ethyls here. So it's not even going to, you taking that from a hash to a wedge does nothing in particular to it. So it's still the same. So if you do that in the process of getting the enantiomer, that's fine. But all you really had to do is invert it at the asterisk. That's all. So there's that one. So that was what's essential to do this one here. But if you just want to think about this, like just take them all, just enantiomer opposite. I can't say I blame you. You know, you might as well just invert everything. That way you don't have to think as much about it. But I hope I explained that well. Do you have any questions? Okay, we're going down to this extra problem, this homework E. This homework problem relate to the homework problem E. So well, I'll see if I can save this for the whole period because I'm asking you to put this down on the left under the 4 molecules there already. Talked about the molecule and now I have to recopy it several times over because this molecule here has 2 chiral carbons. There's 2 chiral carbons, so I'm gonna recopy. It looks like a W. That is to say pentane with on the second carbon at the very left, H is on a hash, the OH hydroxy is on a wedge. At the middle carbon going up, an OH is on a hash and an H is on a wedge. I'm just recopying it. This is highly detailed. So the first problem, the first part of this is just to copy it over accurately, all included. Copying it again. The second carbon at the very left has a hash H down, an OH wedge down, and the middle carbon, we're just recopying it. OH hash up, nothing's happened yet, just recopying it. This is the boring part, H wedge up on the middle carbon. So there are some copy jobs for that. I'll just give you a few moments. That was a lot of copying. Okay, I'm going to get going then. Okay, this is a little bit different take on this because you're seeing we have both the wedge and the hash present. So, but it's just inverting there's this way to do it. Okay, I'm going to invert everything. Okay, I'm going to invert everything. Asterisk, wedge hash, invert them. Asterisk, wedge hash, invert them. You get the enantiomer. Here goes. I can just change the groups, erase the H, erase the OH, take a look back at what you had. It used to be that H was on a hash. Okay, what's the opposite of that? H is on a wedge. Put H on a wedge. Used to be OH was on a wedge. Now the invert opposite is OH on a hash. You can do it like that if you like. Do you follow? Okay. And let's do the other one. Otherwise, it's not the full opposite. So scuff mark, scuff mark. I forgot already. I forgot what's what. So I'm looking back at here. Used to be before OH was on a hash. Now we'll put OH on a wedge and the other one goes there. That's the full enantiomer opposite. Any questions about that? And to do the diastereomer, di is to bi is to half, invert one or more, but not all. I'll show you this way now. Okay. I'm going to choose to invert this one. Okay. I could have chose either. I don't want to do them both, or else I'll get the enantiomer. So I'll choose this one, and you can do it this way. You could switch the bonds. Okay. So I'm erasing the wedge and the hash. You know something I forgot already. I forgot what it was. I erased the bonds, but what did it used to be? OH used to be on a hash. Okay, gotcha. Now let's put OH on a wedge. So you can do it like this if you like. Try to bond to O. See, that was not a good meet up there. So that, yeah. So used to be OH is on a hash. They can change the bonds if you want. You can change the groups or you can change the bonds. Okay, so you pick. But just invert it once. And used to be that hydrogen up was on a wedge. Now I'm going to put that over here on a hash. There, that's good. I inverted one of them, but not everything. So you can change the bonds too, if you like, or you can change the groups. So I would, once you would take a pass through this homework, I would take a look at it to make sure that you didn't make any quick mistakes. Okay, so that would be my recommendation. So it's straightforward enough to do, but you just don't want to make any mistakes and get caught with that. Those are our answers. Do you have any questions about that? Looking for questions? Alrighty, so this is the optional bonus. This has a front and a back. Okay, so you might want to put at the bottom back. That way you'll know this is the optional bonus. So I'm going to do problem probably A, B, and C. if they were letter labeled. They're not, but that would be from A, B, and C for us. Down to the 5 member ring with the chlorine and the bromine, we'll do up to there. And then you can do from the remaining column on that page and then the ones on the back. There's your, there's another way to draw an anchor. Besides recopying it and inverting all what you can have it. So that's to draw the mirror image. I think I'm going to work over here because that's where the camera is. So I'm erasing stuff where we drew the enantiomer by recopying it and we inverted all wedges and hatches. Okay, so you can usually when things are instructed in here, it's try just to keep to one method. As I understand that different methods can be combined, and so. But this is so prominent of a method. I have to instruct it. So my hand is forced. So you can draw the mirror image of anything. Okay, so I'm going to draw the mirror image of a face. Oh, I can scoot over here, and that way the audience knows what's here in that room. So 5-7, another way, another method to draw an enantiomer. Recall, to draw the enantiomer, we just did it, didn't we? We did this 3 times. Recopy the original structure and then invert all wedges and hashes. Sorry, when I copied in the hallway, I pressed color copy and it came out, black and white. And there is an alternate method to draw the enantiomer. That's the opposite, right? Of the chiral molecule. That is, draw its mirror image. And an enantiomer, your textbook author Smith, Janice Gorzinski Smith, goes on to define an enantiomer in the textbook as a non-superimposable mirror image. That's what she defines it as, and others. So we're on this handout here. I'll zoom out that way the audience knows which one we're kind of on, because these, after a while, these get to look alike, all these handouts. So there, we're on that one. Now I'm about ready to draw a mirror image of a profile of a face. Here's the mirror. Someone waking up in the morning. There's the nose, if you will, the chin, and so on and so forth. The eye. Sorry about that picture. I did the best I could. Okay, so you can see that their nose is closest to the mirror, right? Like 3 circles away, 3 open circles away, if you will. And there's the mirror image of the nose. Same altitude, same height. Okay. The nose is at the same height. So far, so good? Okay. And this is what you want to do for a molecule. There's the eye level. This person is looking in the eye at themselves. So, yeah, making eye contact with themselves in the mirror, and goes on. Next back there. If they were wearing a baseball hat, then the brim of the hat would be closest to the mirror, right? Wouldn't it be? Yeah. Don't be too impressed. Okay, so that's a mirror image. All right, any questions? Now, we can do this with molecules too. Let's try it with molecules. Try some of these. And this is the bonus. Please, for the bonus, if you wanted to do that, that would be asked for Monday. And this is a way to draw the enantiomer. I copy that accurately, and we'll do the next one too. next year, you'll be actually generating in a test tube test, a silver mirror, and you can actually take the test tube home, actually. You coat a test tube test, it's called the Tollman's test, and you coat it with silver. And it's a neat, yeah. Yeah, it's neat stuff. The mirrors are made out of silver. And now, I think I'll put this closer to the mirror, and then I think I'll be ready. I believe once you see one, then you'll be set to go, but we'll do more. Make sure I copied it correctly. Yeah, right. Chiral carbon, of course. That would be difficult to figure out if this is R or S because H is not on a hash. But that's not the job at the moment. So the job at the moment is, see the fluorine is closest to the mirror, isn't it? Isn't fluorine F closer to the mirror than H, right? Okay, by that to the mirror. Do this fairly. 4 open circles or such equidistant is the term is used in certain math classes. Equidistant. Fluorine is still on a wedge. Okay, it's coming through. Okay. And you have just above it at the same altitude. There's the answer to the methyl on a hash. There's the answer to that. Hydrogen is highest at altitude. If we were in Colorado, we'll have the highest altitude, that hydrogen there. And back away, it has like an ethyl tail, okay? Like an ethyl tail there. And you're done. That's the mirror image. Do you need the equidistant, so on and so forth, open circles? Nope, you don't need that. So what do you think? Are mirror images okay by you? Okay, let's try the next one then. Here's the mirror. Look how far away. It's open circle, open circle. Oh, this is clocking some miles here, aren't we? So this is a long time until the mirror gets all the way back to the fluorine, right? So that's going to be the same case. So look, this endpoint carbon is so close to the mirror, so gonna be that same way. And I'd like to ask a question now as we get going with this. Is this compound over here a Cardican angle parallel convention? Is this R or S? This chiral center, ranking them 1, 2, 3 priorities. This is R or S. R, okay. Yes, thank you, Jacob. Thank you for your expertise there. It's R, 1, 2, 3, R. So after this mirror does its process, then we will expect the enantiomer would be opposite, right? S. Enantiomer is the opposite. So if you start with R, 1, 2, 3, clockwise, R clockwise, and are expecting over here when it's all finished, is it hydrogen with a hash closer to the mirror than fluorine, right? Wasn't it? It can measure. I can get a roller out of the back room there and measure it. Hydrogen is closer to the mirror, isn't it? It's still in a hash. And fluorine there. So if you did this now, Jacob, you'd find that this is now S with your priorities assigned as such, counterclockwise. That's what a mirror does to a molecule. If it is chiral, if it starts at R, it will become S. And I'm going to walk around the room to see how you're doing with that cyclo compound with the ring. Okay. And if you want to turn this in today, feel free. It's check your answers with respect to that word equidistant. I had a bonus without a name on it. You can blame me. It was one of these con angle pre-log lecture worksheets. One of these things. If you didn't get that back, then I have it. Wanted to claim it. It may not be someone in the class today. Yeah, three good examples to go on. Ones I did and the one that you did not get. And then the rest of them will be asked for my if you so choose. And I'll just type in this other one, and that way you can have more time to do this, you know. So if I do this for the Zoom people, and you can feel free to continue. We'll move on in a minute. So this is the cyclomolecule. 2 chiral carbons, actually. If someone asked you to assign con angle parallel convention for both of them, I know which one, and they told you you only have to do one. Rather than doing both, I know I would do the one with the chlorine on a wedge because that means hydrogen's on a hash. That would make that easier. Otherwise, I have to do a ring flip. In terms of they don't have to be perfect mirror images, you know, like this kind of little, the chlorines aren't like, you know, facing up as perfectly, and but hopefully they can get see a resemblance. This is a mirror. Okay, so you can, if you want to on your homework, you can draw enantiomers based on this mirror device. You don't have to read. You have two choices. You can, to draw the enantiomer, you can recopy and invert all wedges and hashes, or you can do the mirror. So that's your choice as to which one you would like to pursue. I think I'm done with that. So, any questions before we will leave mirrors? Now we'll go back to this handout here because I have to give you some definitions again. They're purple. On blackboard, so there's probably for you. We'll not get through all this today. We won't get through all this today, so we'll so please bring this on next time. You're good, okay. And the handout, which was just handed out. Title called 5-9 compounds with 2 or more chiral carbon atoms. So we're approaching the end of chapter 5. Sheet 1. We have some fill in the blanks, so we'll, I can tell you this: the last class got as far as number 4. We may get further. We'll find out. But I do have 2 things to pass out today. I have to right. I know where I was to do that. We have these name slots, so I provide these definitions for you. So by definition, I am broadcasting sharing with you. A meso compound, meso, mir. Okay, so this that consonant sounding, isn't that helpful? Ironic or something that we're really plucking out with the consonant sound as meso, mir. A meso compound has at least 2 carbons. It could have 6, it could have 8, it could have 3, at least 2, and a sigma that some of you have identified on previous molecules. You can identify sigmas. So this is if a molecule has at least 2 asterisks and a sigma. You didn't know it at the time. Earlier on in chapter 5, I didn't tell you that to you just to try to not tell you too much stuff. But this is a meso compound. And the meso pattern is RS or SR, for instance. 2R, 3S, dibromo-butane. I look at that formula. You could Google it. I look at that, and just because of that pattern, RS or SR, I know that that's a meso compound. That molecule will be expected when I draw it out to have a mirror plane in it. That's handy information. That's the world famous meso pattern. I would hope you would know that, because it can make short work of a lot of problems. It's an insider's tip. Not everyone knows it. Secret. The secret is out. The meso pattern. So this can help. It's handy. It can make quick work of things, as you'll see if you know it. The world famous meso pattern is RS or SR. Very useful to know. I like knowing information that can make quick work of problems and can be beyond hints. Any questions? I'll wait a moment. Another category of compound is called D, L. It has to be little d, little l, if you will. If you're curious, that stands for dextro and levo. If you'll be patient, I'll tell you more about those next week. Pharmacists know about that. If you're going to be a pharmacist as your stock in trade, you would know about dextro, levo. Dextro, levo, and so that's what DL stands for. So it's not, it's called DL. If it's not a meso compound, it's a DL compound. It's a category of compound which have at least 2 carbons and no sigma. That's called a DL compound. And the world famous DL pattern is RR or SS. The world famous pattern is RR or SS, such as 2S, 3S dihydroxy, that's an OH. Butane, 4 carbon is I know that it's going to have no mirror plane with wedges and hashes. Once the wedges and hashes are built in, then I know it doesn't have any mirror plane. Handy, isn't it? Wow, great information. Why that? Anyone need a moment with that? It looks like yes. And now we're going to go to okay, there's your fill in the blanks. I'm going to do it. In a molecule with 2 carbon atoms, a meso pattern will always be RS or SR. Giveaway. I don't have a trick to know that, sorry. I don't have any weak analogies to help you there, or weak tricks to help you. A DL pattern in a molecule with 2 carbons, a molecule which is DL will have one of the asterisks is R and the other asterisk is R. And here we'll be considering just molecules with 2 carbons because it just gets to be too complex if you have more than 2. And you could have a DL compound which has one of the carbons is S, and therefore by necessity, the other compound will also be S. We're going to move on to number 3. Number 3 is not related to number 1 or 2. Oh, here's number 3. May I proceed? Okay, thank you. All right. Thank you for that valuable feedback. The molecule was a molecule in the world exists. You could purchase it. You could Google it. I don't know how much. I don't know how much it would cost for 100 grams, but it's a solid. It's a greasy solid. Look at how many carbons are. Right? 10 carbons. It's greasy. It's like a waxy solid as you open up the bottle. It's 3R, 8R dibromodecan. So the question is, what will be the enantiomer of that? What type of lettering will provide the enantiomer? Does anyone know that answer? The enantiomer of RR is what? Excellent. Yeah, thank you, Julian. There is consensus. SS. First, you both are. And enantiomer is opposite, right? That's your hint there. E, the vowel, opposite, you can put O. And a diastereomer, that's that business of a di is to bi is to half, invert one or more, but not all. Of what? Of the RR. Invert one or more, but not all. So you can take it RS or another perfect answer is SR. You can leave the numbers out. You understand? Di is to bi is to half. You're probably saying like, oh, like what is this diastereomer? Like, well, why is that interesting? I'll let you know next week. It has to do with physical properties. We're getting into like why pharmaceutical drugs are so expensive. So, but if we can get down now, like the definitions by drawing molecules, then I'll tell you the context. Okay, that's the idea. All right, so number 4. I hope you can answer this. It is related to what I talked about today. A molecule is 3R, 8R dibromodecan. That's the same molecule again. Is it going to be meso or is it going to be DL based on its lettering? You know, Julie?
DL.
DL, thank you. Well, then they put this question in there for us. Draw a line angle formula. Oh boy. What am I drawing? I'm drawing a DL compound. What is that? This will have 2 carbons and no sigmas. I will need wedges and hashes to do this. I'll need to have my answer be with wedges and hashes somehow in order to provide to my audience that there is no mere plane. I'm going to do that on the marker board. We're going to draw 3R, 8R diagram. This is kind of where the last class left off. I'm going to go to the marker board now. I'm going to pay attention here and do that. Bromo is bromine, Br. 35 protons. I'm going to erase this. Yep. I know you can draw a decane, it's 10 carbons, but if you draw it so that it's zigzag up, down, up, down, up, down, this could be not helpful, you know, so that may not be the best course of action with respect to mere planes and stuff. So let's draw it as a descending staircase and an ascending staircase. Did I do 10? That's good. That's a good tool to have in your toolbox. So this allows us to see the mere plane all the more easier. So here's 3, here's 8 of that 10. So this is something that is nice to access a method by which to draw main chains, which if you need to. I think you could still answer the question with the zigzag, but I want to show you this. Bromine, bromine. So I have the 2 chirocarbons at such locations here. Asterisk red, asterisk red. Questions from you? And we reportedly, as I said, have 2 chirocarbons and 0 mirror planes. Yep. So we have the 2 chirocarbons. In order to show the audience that I have 0 mirror planes, and I have to have one of these be a wedge, one of these be a hash, right? You can pick which one. Oh, I forgot to do this with the other class. I can do it with you because there's time enough. Let's put this to the test. Is this R or S by your cone angle parallel convention? Sinclair, do you know? One on the left. What's the first priority? Yep. And the second priority is going to be the longer chain, kind of like right here. Third's here. Yep, looks like an S. What did it want? RR? Okay. And if it, so this is DL, isn't it? So far, so good? Thank you, Sinclair. You helped me figure out this is S. So if this is DL, right, and this is S, right, then this must be S. Oh, that saves me some work. I don't have to do any rotation. Hooray. But this is the wrong answer, right? We need RR, don't we? We need the RR. So, oh man, I must not be lucky today. If only I had that one be a hash and this one be a wedge, then I would have lucked out and gotten that. So just to answer the question which was asked, which I don't, this would have been nice. I had a 50-50 chance, but, and now you can see that there's 1, 2, 3. This is R. If this is DL, no mirror plane, and that's R, then that pattern, I love it. That's also R. Saves me some work. Oh yeah, your homework. That'll take us to the end of today's class. So I'll pass back to this homework first. This will be asked for Wednesday. So you could, if you want to turn it in on Monday, feel free. Just asking for Wednesday. If you're drawing an instrument, and drawing experiments, and drawing compounds, have all of them. Yes, please. Here are your tests. Be available until like 1 o'clock today. I'll turn this off.